Hello students, welcome to my YouTube channel. In this video lecture, I am going to answer questions from sample paper number 4, RK Bali navigation book. In the previous lectures, I solved the first 60 questions. In this particular lecture, I am going to answer the next 10 questions, beginning question 61 up to question 70. This is the 4th edition book. If you have any other edition book like the 5th, the 6th or the 7th one, no problem. The questions still continue to remain the same. So now let's start with question number 61. The limits of the yellow scale of an airspeed indicator are what? So options A, B and C are given. So this is your airspeed indicator. You can see there are 4 different colors: white, green, yellow and red. Now the white arc here, okay, the white arc represents flap operating speeds. Okay, I'm writing flap speeds. Next, the green arc here is the normal operating range or normal operating speeds. Normal operating speeds. Next, the yellow here is the range, caution range, and the red line here is the never exceed, never exceed speed. Okay, never exceed speed. Now, this white arc has a lower limit and upper limit. Now the meaning of this the lower limit of the white arc is VSO. That means stall speed of your aircraft in landing configuration. Meaning when flaps are extended to landing position, landing gear is extended down. Okay, so that is VSO. The upper limit of the white arc is VFE. VFE, that is flap extension speed. This is the maximum speed at which you can extend your flaps. And then after extension of flaps happens, you can operate your flight with that flaps in extended position only in the speed range which is white in color. So beginning from the lower limit of the white arc to the higher limit of the white arc, you can operate your aircraft at any speed in that particular white arc. Next, the green range or the green arc. Now the lower limit of this green arc, okay, the lower limit of this green arc is called VS1. Stall speed of your aircraft in clean configuration. Clean configuration means when flaps are not extended, they are fully retracted. And if your aircraft has retractable landing gear, that landing gear is retracted in the belly of aircraft or inside the fuselage. So that is clean configuration. No flaps, no landing gear, nothing. Okay, so stall speed of your aircraft in clean configuration. Next, similar to the white arc, this green arc also has an upper limit. The upper limit of this green arc is called VNO. That is maximum speed that you can maximum speed in the normal operating range. Okay, normal operating range. Now you can exceed this VNO, maximum normal operating speed, only in still air conditions. So if you want to exceed the speed of your aircraft and enter this yellow color range, yellow arc, yellow range, which is your cautionary range, you can only do that if the atmosphere is calm and stable. Okay, if you exceed the speed of your aircraft beyond VNO and enter the yellow range or yellow arc, you can tend to tendency possibilities are you can impose many loads on your aircraft. So make sure when you exceed the VNO speed and enter yellow color range, the atmosphere is still, the air is still. Okay, so yellow range is the caution range. Now the lower limit of the yellow range or yellow arc is the higher limit of the green arc. Okay, so the limits are common to both of them. The VNO speed, this limit is common to the yellow arc as well as the green arc. VNO is the upper limit of the green arc, whereas for the yellow arc, VNO becomes the lower limit. And the upper limit of the yellow arc yellow speed range is this red line. This red line is nothing but VNE, never exceeds speed. So the lower limit of the yellow arc is VNO and the upper limit is VNE. So let's look at the question now. The limits of the yellow scale of an ASI are VNO for the lower limit, VNE for the upper limit. So that's wrong. We have VNO, November Oscar, not LO, Lima Oscar. So that is wrong. Uh, VNE for the lower limit, VNE for the upper limit. Charlie is VFE for the lower limit and VNE for the upper limit. So maybe there is some printing error here. 61. Yeah. So there is a printing error. Now in place of VNE for the lower limit, VNE for the upper limit, it should be VNO for the lower limit and VNE for the upper limit. Okay, so there is some printing error, but in exam, remember, you will mark that option which has VNO for the lower limit and VNE for the upper limit. Next, question number 62. A Mach meter comprises of what? A combination of ASI, which is airspeed indicator and altimeter, a combination of vertical speed indicator and altimeter, at airspeed indicator with its scale marked in Mach numbers. So the correct answer here is option A. Your Mach meter is a combination of two instruments, airspeed indicator and altimeter. Next, what is the true airspeed at 40,000 feet? ISA temperature in the ISA atmosphere. You are flying at Mach 1. Now, what is the formula for Mach speed? Mach speed equals to true airspeed divided by local speed of sound. Now, the local speed of sound is 39.17 square root of temperature in Kelvin. Now, we are flying at 40,000 feet. We are flying at 40,000 feet. So, ISA temperature at 40,000 feet will be equal to 15 degrees Celsius minus 2 into 40,000. So 15 minus 80. So 15 minus 80, 10, 70 minus 65. But now since we are flying in the ISA temperatures or ISA atmosphere, we know the rule of that particular ISA, what ISA states. The rule is that above 35,000 feet, okay, all temperatures are going to remain constant. That means when you fly above 35,000 feet, 35,060 feet, all atmospheric layers will have a constant temperature, of minus 56.5 degree Celsius, right? So 40,000 is more than or above 36,000 feet altitude, right? So the temperature at 40,000 feet, we are going to consider temperature of minus 56.5 at 40,000. But the real should be, according to jet standard atmosphere, it should be minus 65. ISA assumes constant temperatures above 36,000. So minus 56.5 degrees Celsius at 40,000 feet. What will be the Kelvin temperature? Minus 56.5 plus 273 equals to 216.5 kelvins. So this is nothing but equal to 216 Kelvin. So let's substitute the values here. Local speed of sound will be 39.17 square root of 216. So 39.17 square root of 216 is 14.69. So 14.7 approximately. When you multiply that, you get an answer 575.67. So approximately 576 knots of local speed of sound. So true airspeed will be your Mach number, which is 1, multiplied by local speed of sound, which is 576, So true airspeed will be 576 knots. Correct? So the closest option here is option Charlie. You can also solve this question using your CX3. Question 64. What happens to Mach meter indications in a constant rectified airspeed climb? Constant rectified airspeed means constant calibrated airspeed climb. So now let's say this is your atmospheric layer. You are climbing in this layer, okay? Our aircraft is climbing in this layer. Now as you climb to higher and higher altitudes, what happens? Atmospheric pressure, atmospheric pressure decreases. Atmospheric pressure decreases. Now we all know that your airspeed indicator is a pressure instrument. It's a pressure instrument, correct? So that means it's a pressure instrument. It registers dynamic pressure, and this dynamic pressure is represented to us in the form of airspeed indication in terms of knots. Okay, so airspeed indicator is a pressure instrument which registers dynamic pressure, and this dynamic pressure is nothing but our speed in terms of knots. Now, what kind of speed are we talking about? We are talking about indicated airspeed, which when corrected for position error, pressure error, is your calibrated airspeed. Okay, so the indication given to us by the instrument or by the indicator is a calibrated airspeed. Now, when you climb to higher and higher altitudes, air pressure decreases. If atmospheric pressure decreases, the dynamic pressure registered by your airspeed indicator will also automatically decrease. Right? You may be flying at a you may be flying at a particular true airspeed. Okay, true airspeed of 200 knots, constant true airspeed of 200 knots in your climb. Let's say. Okay, your true airspeed of 200 knots. But as you climb to higher and higher altitudes, your airspeed indicator is unable to register the same dynamic pressure which it was able to register at lower altitudes, because as you climb to higher altitudes, atmospheric pressure decreases. Okay, so there is insufficient registration of pressure in the pressure instrument, which is your ASI. As a result, airspeed indicator will show an indication which is much lower than actual speed of aircraft. Okay, so the calibrated airspeed. So as you climb to higher and higher altitudes, as you keep climbing to higher altitudes, calibrated airspeed decreases. Okay, calibrated airspeed decreases because atmospheric pressure in which you are flying, pressure decreases. So airspeed indicator receives pressure inputs, and these pressure inputs are have corresponding outputs in terms of airspeed indicator, that is knots, calibrated airspeed. So if inputs decrease in value, outputs will also decrease in value. Okay, so in order, so what is the this is the problem. Let's say this is the problem. As you climb to higher altitudes, your calibrated airspeed decreases. Okay, so the solution is that when you know that your calibrated airspeed is going to decrease as you climb to higher altitude. So what you're going to do is at you're going to increase that true airspeed. You're going to increase that true airspeed. So what will happen now? Like I said, atmospheric pressure has decreased as you climb to higher altitudes. Now you will increase. The solution to this is you increase the true airspeed of your aircraft. Instead of flying at constant true airspeed of 200 knots in your climb, you increase that speed to 250, 240 knots, whatever. As you increase the speed of your aircraft, the forward speed of your aircraft, the dynamic pressure generated or the dynamic pressure registered by the airspeed indicator will also increase. This increment which is brought by increase in true airspeed will compensate for any decrease in atmospheric pressure surrounding your aircraft when it flies to higher altitudes. Okay, so now you cannot, or you yourself cannot increase the atmospheric pressure around your aircraft. So the only solution is that you increase the true airspeed of your aircraft. As a result of that, impact pressure increases, dynamic pressure increases, and this dynamic pressure will be registered as increase in calibrated airspeed. So therefore, if you want to remain in a airspeed, constant calibrated airspeed climb, you don't want your airspeed indicator to show a drop or to show a decrease in value. What you have to do is you have to speed up or increase the true airspeed of your aircraft. Okay, this increase in true airspeed of your aircraft will keep your calibrated airspeed from falling in value. Okay, so this is the explanation. What happens to Mach meter indication in a constant rectified airspeed climb? Now, so like I said, in a constant rectified airspeed or calibrated airspeed climb, your true airspeed increases. Mach number is proportional to true airspeed, correct? So if true airspeed, because Mach number is nothing but true airspeed divided by local speed of sound. So if true airspeed increases, Mach number will also increase. So option A is the correct option. Now, question 65, factual question. Make sure that you read all the gyroscopic chapters from your RK Bali book. Okay, especially the degrees of freedom, number of gimbals, the what kind of gyros they use, like that. So the characteristics of DGI used in a gyro stabilized compass are 1 degree freedom vertical axis aligned with a real vertical by automatic erecting system, 2 degrees of freedom horizontal axis then maintained in the horizontal plane by automatic erecting system. Again, 2 degrees of freedom axis aligned with vertical maintained by an erecting system. So option D is the correct answer. Your DGI has 2 degrees of freedom. It has horizontal axis, not vertical axis, and it is maintained in horizontal plane by an automatic erecting system. Next, question 66. Radio wave ground attenuation is greatest on what frequency? Now, what is attenuation? Attenuation is loss of signal strength as the signal travels outbound. Okay, as the signal travels away from the transmitter. Now, this radio wave ground attenuation is greatest, attenuation increases as the frequency increases. So, out of the three bands here, option A will be the correct option. Question 67. When aircraft has turned 360 degrees means complete rotation, coming back to the same point after making a full 360-degree circle, okay, with a constant attitude. So your attitude of your aircraft is same, straight. If you are making a full 360-degree turn straight with your pitch attitude maintained or aligned with the horizon, so that same pitch attitude you are going to maintain throughout your turn. If you decide to make a climbing left 360-degree turn, so the attitude of your aircraft will be above the horizon. If you decide to make a descending 360-degree turn, the attitude of your aircraft will be below the horizon. Whatever attitude you select or you choose to fly with, you're going to maintain that attitude constant throughout your 360-degree turn. And again, constant bank. So if you enter your angle, if the angle of bank that you choose to make a turn is 20 degrees, you're going to maintain that 20-degree bank throughout the turn. The pilot observes following on a classic artificial horizon. So what will pilot observe? Too much nose up. So after making a full 360-degree turn, what will artificial horizon indicate? Will it indicate too much nose up? Okay, so extra pitch up attitude more than required, but correct bank angle, too much nose up, and too high a bank angle information more than required or more than expected. Attitude and bank angle correct. So attitude will be also correctly displayed, bank angle will be also correctly displayed. So this is a screenshot from the Oxford Instruments book. You must remember these points for your CPL, ATPL and airline exams as well. So here they have given, if you make a 90-degree turn, your artificial horizon underreads the bank angle. So let's say you're making a left hand 90-degree turn at a bank angle of 20 degrees. So after the completion of the turn, your artificial horizon will show underread the bank angle. Underreading the bank angle means it will show the information of bank angle which is less than expected. So if you are making a 20-degree bank angle, the information provided to you will be less than 20 degree, 15 degree, 18 degree, something like that. So underreads bank angle. As for pitch attitude, the pitch error indicates a climb. So if you are making a 90-degree turn, after the completion of a turn, the artificial horizon will indicate a attitude. Pitch up attitude. Turn through 180 degree. When you make a 180 degree turn, after the completion of the turn, the bank angle will be correct. So if you enter the turn at a bank angle of 20 degree, at the end of the turn, the bank angle indicated to you will continue to remain 20 degree. Pitch error, again it will indicate a climb. Artificial horizon will indicate a climbing attitude. Even though you might not be in that climbing attitude, but the information generated or provided or represented to you is climbing attitude. Turns to 270 degree. So in that case, your bank angle will be overread. That means if you enter a turn at 20-degree bank angle, after making a 270-degree successful 270-degree turn and completion of the turn, the bank angle will be overread. That means you are making a turn at 20-degree bank angle. The information provided to you will be more than that, 25, 30 degree, whatever. Pitch error. Again, pitch attitude will be a climbing attitude. Next, turning through 360 degree. So when you make a complete 360 degree turn, the bank angle shown to you will be correct as well as the pitch angle will be correctly displayed. So the tilts are of the order of 2 degree. The setting of the horizon, that's okay. So remember these 4 points, 90 degree, 180 degree, 270, 360 by heart. Okay. So according to this information, if you make a 360 degree turn, your attitude and bank angle will be correct. Question 68. When aircraft has turned 270 degrees with a constant attitude and bank, the pilot observes following on a classic artificial horizon. Too much nose up and bank too high, too much nose up, bank too low, attitude and bank correct. So answer is too much nose up and overreading of bank angle happens. So 270 degree overread bank angle, pitch error indicates a climbing attitude. Next, artificial horizon has 1 degree freedom lateral spin axis, 2 degree freedom vertical spin axis, 2 degree freedom horizontal spin axis. So the correct answer here is 1 degree freedom lateral spin axis. How will a basic artificial horizon respond if aircraft performs 270-degree turn at constant bank and rate of turn? So similar to the previous question, nose up and bank, nose down and bank, nose level and bank. So when you make a complete 270-degree turn, artificial horizon incorrectly or erroneously indicates a climbing attitude and the bank angle shown to you will be more than required. So correct answer here will be option A. So this concludes our lecture. I hope you have understood all the 10 questions I answered in this video lecture. I hope you have understood the explanations. Do watch all my previous video lectures in which I have solved questions from other sample papers, sample paper 1, 2, 3, 5, 6. Okay. If you have any doubts, comments, questions, let me know in the comment box of this video. I request you all to subscribe if you haven't yet. Share this channel with your friends who are also preparing for various exams and hit the like button if you have liked this video lecture. Thank you for your time.